PCS members and friends to our today's IBS PCS seminar. It is a great pleasure to have with us today Professor Andrei Bernevig from Princeton University. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yeah, thanks, Dylan. So today we have Andrei Bernevig from Princeton University with us, talking about the exact map. Exact map between the twisted bilayer graphene and multilayers and topological heavy fermions. So let me very briefly introduce Andrei. So he received his PhD from Stanford University and then was a postdoctoral fellow at Princeton University and is now at Princeton as a professor. And he is famous for his works on in condensed matter on topological insulators, superconductors, and also semimetals. And so with this, Andrei, the screen is all yours, so you can start.
Thank you. Thank you so much for inviting me. Sorry about probably what's going to be some coughing during the talk because I'm just getting over COVID. Thanks for your understanding. Now, I should share the screen, right? Let's see.
Yes.
Okay. Fantastic. Okay. So let's see if this is working. Okay, so I wanted to basically talk today about something I've been very happy about, which is maybe not so well known, but just very dear to my soul, which is this mapping between twisted bilayer graphene and a topological heavy fermion problem. And this is really kind of remarkable for twisted bilayer, I think. But I think it might be even a generic method to understand some of the flat bands that appear in many systems, especially the twisted ones. The key person in this idea is actually Jida Song, and now was a professor at Peking. And now this idea has also been taken and developed by Jonah, Dimitri, and Andrei. And of course, there's these more senior collaborator experimentalists that we've all benefited from talking to, which are in the second row. So I'm going to start with an introduction, but the introduction is going to be a bit brief. The talk is about the physics of the lowest bands around charge neutrality of two layers of graphene, which are stacked together on top of each other and rotated by a small angle. So it turns out that, to make a long story short, if you take two layers of graphene and rotate them by an angle, actually, sorry, I lost my mouse. Okay, now this. Sorry, I started annotating and I lost my mouse. I'm having technical difficulties. I shouldn't annotate. Do you know how to get out of annotation if you don't see your mouse? Control.
Perhaps upper part of the screen.
Maybe you can unstop sharing and I can start resharing. Mm-hmm. Like somehow I thought I had this problem solved, that I could see the mouse and annotate, but apparently I cannot anymore. Zoom changes settings every. Okay, fantastic. Now I have my mouse back. So very good. So now I won't annotate anymore. Maybe I can try again with a pointer just like 1 second. Maybe I can try with the pen. Let's see. Okay, now it's working with a pen rather than annotation. Thank you. Thanks for this. Okay, so after that short innuendo, you take 2 layers of graphene, you rotate them by a small angle, and at some angle, which is called the magic angle, which was found in the Bistritzer-MacDonald paper and also by pointed out by some other people, this physics such as Paco Guinea and others, Castroneto. But the magic angle value, which was given in this paper, which is around 1.5 degrees, basically leads to the appearance of these remarkably flat bands in the electronic spectrum of the graphene. And notice that this is the moire Briand zone. So now you get a new periodicity. This is a rather large angle, actually, that is shown here. At 1.05 degree, the periodicity is much larger. The Briand zone is much smaller. And in this Briand zone, you get a series of bands that are very flat. Now, you get also some dispersive bands, and this velocity of these dispersive bands is basically that of the Dirac fermions of the original graphene. But the appearance of these very, very flat bands leads to interesting consequences. The consequences are the following. First, we have to count how many electrons we can put in these bands. Now, it turns out, for reasons that I'll explain in a little bit, that there are several symmetries in this problem. First of all, there's a spin symmetry, which leads to the factor of 2. Then there's a valley symmetry, which leads to another factor of 2. And then there's 2 bands, because like in graphene, I have Dirac fermions, even at the moire K vectors. So this is all these are moire vectors. So there's another 2 bands. So in total, there's 8 bands separated in quantum numbers that we'll explain in a little bit. But these 8 bands can, of course, in single particle theory, be occupied by 8 electrons, which will count from -4 to 4. And counting from -4 to 4 means that we can basically gate tune this system, now being that this has much lower density because it's much larger in itself, so you can gate tune it much more easily than normal graphene. You can gate tune the system from the single particle gap, which sits here, which is at filling -4, to the next single particle gap, which sits here, which is at filling 4. And normally, as you gate tune the system through -4, -3, -2, all the way up to 4 electrons, you should see a metal from -4, it's an insulator, to 4 electrons. However, the phase diagram, experimentally seen, looks something like this. And it's a bonanza of many body states. So for example, at every integer filling, instead of seeing a metal, you see an insulator. Now, at every integer filling is a made-up statement. You see insulators in different samples at different fillings. Most samples see insulators at filling 2 and filling -2. So those are very clear. Now, depending on whether your sample is aligned with the boron nitride substrate or not, you can see insulators at filling 3 and -3, etc. And some samples see insulators at filling 1, etc., -1. But there are insulators features, at least, at and clear insulators at some or all integer fillings of electrons. Moreover, in between these insulators, you see superconductors, and this is actually a kind of phase diagram, which is reminiscent, obviously, of the cuprate phase diagram, except now you have the tunability that you didn't have in the cuprates to tune this electron number and look at the properties of the system in a sample that is the same, rather than dope it with different dopants and look at different dopings such as you have in the cuprates. And moreover, there's all kinds of other behaviors, such as strange metal behavior at large temperatures. Then in STM, there's quantum dot behavior in tunneling studies. And then some of these insulators that you can see here are actually Chern insulators, so the correlated topological insulators, or at least close to correlated topological insulators, as we'll explain in a little bit. Moreover, in kind of two large classes, the experiments in this field can be characterized by the following juxtaposition. Some of the experiments see quantum dot behavior. So, for example, if you do STM, as I said, you can see a highly localized charge at the AA stacking of a twisted bilayer. So the AA stacking would be actually the center of this hexagon. So this is the AA stacking here, and the AB stacking would be this. So we're going to call these two regions the center of the hexagon, the C6 invariant. We're going to call it AA stacking, and AB stacking is the C3 120-degree rotation region. So at this region, you see high at the triangular lattice, basically, not at the hexagonal lattice. You see high concentration of charges. And moreover, if you tunnel there, you basically see a huge on-site repulsion. So all the Hubbard physics, maybe not Hubbard physics, but certainly the interaction physics is concentrated at the AA sites. Moreover, you can see some other effects, such as Pomeranch effects, large entropy in the order phase, which disappears under magnetic fields, basically features of loosely coupled local moments. And this picture is really obviously contradictory to the picture, to the phase diagram seen in transport, where you see metallicity and superconductivity, and then you see Landau fans with different Chern numbers and other, obviously, itinerant electron behavior. So understanding this contradictory picture in a full framework has been, to say the least, non-trivial. And I'll explain why it has been non-trivial in the following slides. But this is what we had set up looking at the experiments to do. So if we're going to look at this from a phenomenological point of view, which is not what we're going to do in the end, we're actually going to look at it we're actually going to do an exact mapping. But if we were to look at it from a phenomenological point of view, this picture of loosely coupled moments, local moments, quantum dot behavior, and itinerant electrons would immediately suggest a heavy fermion description. Now, the heavy fermion physics would have to, again, contain some heavy elements, which we'll call f-electrons, which don't really, there's nothing, all graphene is p orbitals, carbon p orbitals, really, just a huge amount of them. But we're going to call these made up heavy elements f-electrons, and some c-electrons, which are some conduction electrons, some itinerant electrons. And this juxtaposition, if we find it, should explain some of these contradictory pictures. Now, what we actually found was an exact mapping between the twisted bilayer graphene, and I'll show you trilayers and multilayers. It's actually a generic mapping, and a heavy fermion model coupled to topological conduction electrons. And all these parameters are calculated in the first principle way, in the sense that from the model of twisted bilayer graphene, which is the Bistritzer-MacDonald model, you can derive the values of these parameters. Now, by numerically. Now, in further work unpublished, we have a way to analytically find these parameters, so you don't even need to do numerics for it. And this model basically gives you a separation of scales of which electrons are responsible for the interactions, for the large interaction physics that's observed in this system, and which electrons are responsible for the itineracy and topology of this system. And a lot of the results that were obtained in Hartree-Fock or strong coupling pictures can now be understood in a very simple, intuitive way. And you can have new insights into the superconducting transition superconducting gap and transition temperature, although I don't claim that is yet a solved problem even in this formalism, because it's still a very hard model to solve. So basically, we're going to get an Anderson model of a heavy fermion coupled to conduction electrons with extra terms, and the conduction electron is going to be a little bit special. So I'm going to go through the construction of the model, And then I'm going to go through a new understanding of the correlated states, and maybe if I get to the end, new insight into new physics. But what I wanted to go is through the construction of the model, because I think this is kind of generic for a lot of flat bands that have small gaps to other bands, which is the generic case in constructing flat band materials. So normally, if I have a flat band, I could potentially think that it comes from localized electrons, which do not tunnel to each other from side to side. So very localized electrons will certainly have a flat band because there's no tunneling, there's no bandwidth. Now, why is there a problem to describe the flat bands in the Bistritzer-MacDonald model or in the model of twisted bilayer graphene in this way? The problem is because of something that's been discovered in the past 15, 20 years, and this is topology. And to understand this, we have to look at the symmetries of the Bistritzer-MacDonald model. So I'm going to go through this a little bit fast, but it's not entirely necessary to understand all the symmetries, but it's good to get a hint of it. So what happens in the Bistritzer-MacDonald model of twisted bilayer, or in, I would say not just in this model, but in all this class of models of twisted layers with a small angle, is that a new symmetry appears. And this symmetry is an emergent symmetry, and it's a valley symmetry. And I can explain really quickly why it appears, because basically you form a new Brion zone, and this new Brion zone has its own valley, and to couple it to the other valley of the original graphene lattice, you need to tile this small Brion zone many times over. And to tile it many times over means a large ordering perturbation theory. So let's understand this. So here, as you can see, I have the Brion zone of the lower graphene layer. This is the large Brion zone here, this large Brion zone. And then I have the Brion zone of the upper graphene layer, this other large Brion zone. And then each of them has a derived fermion here and here. This is from the K point of the lower layer, K point of the upper layer. This is the K prime point of the lower layer, K prime point of the upper layer. So there's 4 derived fermions per spin. So I'm not counting the spin, which is assuming spin orbit coupling is 0, which is almost is. So always keep in mind there's a factor of 2 times spin. So I have 4 derived fermions that basically enter my low energy physics. And if I didn't have any coupling between the layers, that would be the physics. Now I have coupling between the layers, and it turns out that the coupling between the layers obviously is much smaller than the in-plane coupling. So now let's understand the physics. If I take these 2 derived fermions, okay, I form a new Brion zone, which is given by the difference in the wave vector between the rotated K points of the lower and upper layer. And this is, if this is the Dirac momentum of the small graphene lattice, the large Brion zone, then this Q is KD times theta, roughly. And this small gray Brion zone is the Brion zone of the moire lattice of the new large periodicity lattice. And I form another Brion zone around the K prime point. Now, in order to couple these points, I would basically have to tile this Brion zone many times over this large momentum difference, KD. Okay, now this drawing is not drawing the scale. Theta here is not 1.5, but if it's 1 degree, this 1.05, then this Brion zone would be very small. This Brion zone would be very small. To make them couple, I would have to basically do perturbation theory and tile them across a wave vector of order KD. Okay, but these Brion zones are KD times theta, so I would have a perturbation theory in T between the layers, so T perpendicular over T parallel to the power 1 over theta, which is the amount of times I have to tile them from one K point to the other K point of the original graphene lattice. This perturbation theory is, of course, exponentially small as the angle gets smaller. So now I have a valley symmetry. And this valley symmetry in twisted bilayer allows me to look at the single particle model just in one valley. The one coupled, the one of the K point of the lower layer and of the K point of the upper layer coupled by interlayer coupling. And this has an emergent symmetry in the sense that if the original symmetry of graphene involved time reversal, this per emergent symmetry model of Moiré lattice doesn't have time reversal. Why? Because time reversal changes the momentum K to the momentum K prime of the original graphene lattice. So it actually switches values. So the entire model, if I bring in the two values, has time reversal, but the two values are decoupled. So if I want to just focus on one value and understand one quantum number, value quantum number, then the model doesn't have time reversal symmetry, but it has a new time reversal symmetry, which is C2 times T, which gives basically a new type of topology, as I'll show in a new slide. Okay, so this model has C2T symmetry and it has some other symmetries. Now these symmetries are given here, okay, per valley model. And what it turns out to be the case is that, yes, there's a question.
Sungjong, please unmute yourself.
Yeah, I'm wondering if the, I mean, in this, like, do I have to assume the commensuracy of the lattice or not?
That's a very good question. You don't. So these angles do not need to be, so commensuration of the lattice happens at, you know, some angles. Now, of course, I can get very close to any, right, 1.05, I can get very close to any commensuration, but this is a continuum model and it's an emergent translational symmetry. So you don't have to assume commensuration of the lattice. So if you just take, the remarkable thing is if you just take two layers of graphene, plot them and twist them a little bit, just at a random angle, you'll see a new pattern, even though you haven't, you know, hit an exact commensuration. So that's a very
the small Brillouin zone is well defined.
That's right. That's right. That's
Okay.
right. If I have a you know 60-degree angle or whatever, then it becomes important to have commensurate. But the small angle, you'll see the magic of Moiré happens that there's an emergent translation symmetry. It's a very good question.
Okay. Okay. Thank you.
Thank you. This is very important. So now you have in this model, you have several. So in this model, we can now look at the flat bands and describe them by eigenvalues of these symmetries, okay, which is C3Z, C2X, etc., and C2T, which basically complex conjugates eigenvalues. And the eigenvalues of these symmetries are such that these bands have the following eigenvalues, and you can prove this. That this is true for any angle, any small angle. This is actually another beauty of this problem. It's not depending on the model. You can actually prove that whatever model you have a small angle, these are the eigenvalues of the Moiré bands in the Moiré-Brillouin zone. Now, why is this important? To make a long story short, we know what all the eigenvalues of the atomic limits for all the bands in all the symmetry groups are. So what do I mean by that? If, remember that I said that if a flat band comes from localized orbitals, then you know I can understand why it's flat, because it can come from localized orbitals. The problem is that localized orbitals, once you tell me which localized orbitals I have, I can tell you exactly which eigenvalues the bands have in momentum space. And it turns out that none of the eigenvalues of any localized orbitals in this space group match the eigenvalues of these bands. Hence, the bands have to be topological. So it turns out that because the bands are topological, they cannot be described by localized orbitals. So there goes our way of describing, of trying to understand the local physics in twisted bilayer by a localized model. We cannot describe it in terms of localized orbitals, respecting all the symmetries of the lattice. Now, it turns out that I don't want to go a lot into it, but it turns out that the model is even more special in the sense that it has an interesting stable topology. It's actually topological at any bandwidth. So not only taking these lowest, this is the same thing plotted on a much larger energy scale, same band structure. These are the flat bands here. Okay, so if I try to see if these two flat bands are topological, we already proved it. Their eigenvalues don't match any of an atomic limit, hence they have to be topological. But then now we can try to see whether these bands are topological. So we take more bands, okay, and it turns out that they also are topological, and you can see this by what's called a Wilson loop argument, basically plotting the Berry phase of these bands as it winds in the Brillouin zone. So it turns out that the actual key point of the graphene model is the existence of 4n+2 Dirac points in any bands taken between energy E and energy minus E. So if I take any set of bands between energy E and energy minus E in the Bistritzer-MacDonald model of twisted bilayer graphene, or in any small angle model of bilayer graphene with an extra symmetry that's particle hole that's actually also emergent in these models, then I will have 4n+2 Dirac points in these bands. I can never have 4n. And these, 4n+2 are basically, the two of them are at the k-moire point of graphene, of the moire lattice of graphene at k-moire prime. These are these two. And all the other four can be spread out into the other bands. So a lot of this work in understanding these models with these Dirac points has actually been done in these papers, especially actually by Bamyang. And now there's many consequences of this that are not one go through. Also for the superconductivity, for example, there's some prediction that the superconductivity in these bands has to be gapless because of this topology. So we understand the model is topological, so we understand that you cannot write it down in terms of localized states, but we also see the experiment. And the experiment clearly shows us that there are local charges in it. So we can ask, where do these local states actually come from? So now, if you look at the Bistritzer-MacDonald model, and instead of taking, or the graphene model, instead of taking just these two flat bands here, you take the next 6 bands, and you only need this energy range. By the way, this energy range is smaller than the Hubbard U in the problem, meaning this band gap experimentally is smaller than the Hubbard U, so you're justified in taking these. Then you will see that if you add these representations together, so now I have more freedom. I have 2 other representations of the bands that I added together, these gamma 3. If I just now add these representations together and go back and ask, can I write now just axiomatically these bands in terms of localized orbitals? Turns out now you can. And you can see that px, py orbitals on the triangular lattice, so this is the first good thing, that they're on the triangular lattice, this is the only option, give you the symmetries, give you the correct eigenvalues if you add these gamma 3. So you see, they have the atomic limit of px, py orbitals on the triangular lattice has this representation at the k point, has the m1, m2 representation at the m point, and has the gamma 3 representation at the gamma point, right? So basically the culprit were these gamma 1, gamma 2 representations, which are some crystallographic representations that differ by the eigenvalue of C2x, doesn't really matter, it just they didn't fit in an atomic limit. But now if I borrow some of the upper representations, now I can build an atomic insulator, or an atomic band, exactly on the triangular lattice. So let's go and do that. So we choose trial Gaussian type wave functions, px plus ipy, introduce them into Vanier 90 with the Bistritzer-MacDonald band structure, perform maximally localized Vanier states, and obtain the following result. Obtain Vanier states that are localized with 0.2 of the Moiré lattice, so extremely localized. You can see how these look very similar. Okay. And the hopping between them is 0.1 milli-electron volts, so very small. So these are very localized. So these are very localized states. Now we know that they cannot describe all of the Bistritzer-MacDonald bands because they have the gamma 3 representation at the gamma point and not the gamma 1, gamma 2 representations. Gamma 3 is a two-dimensional, gamma 1, gamma 2, both one-dimensional. They don't have the gamma 3 representation, the gamma 1, gamma 2 representation the Bistritzer-MacDonald bands have. Now, because of this, they cannot describe the entirety of the twisted bilayer flat bands. But how much do they describe of it? So if we compute how much they describe of it, it turns out that there's actually a staggering 96.6% of the flat bands are made out of these orbitals. So most of the Bistritzer-MacDonald bands are these localized orbitals, turns out. And hence we conjecture, now we'll prove that the correlation physics must come from these flat orbitals, which they're localized and they'll have high Coulomb, as we'll show. And these are called the f-electrons or the heavy fermions. Now, we want to model the 4% of the remaining states because we couldn't get, if we just had these localized electrons, we couldn't get superconductivity. The 4% of or topology, the 4% of the remaining states can be modeled in the following way. At the gamma point, we know that the f-electrons, the localized states, have the wrong representation. So we know that they have a gamma 3 representation, whereas the flat bands of the Bistritzer-MacDonald model has gamma 1, gamma 2. But we took these 6 bands together per valley per spin. Hence, and we use 1 gamma 3 representation or 2-dimensional representation to obtain the localized electrons. So now we're left over with 1 gamma 3, the other one, for example, and gamma 1, gamma 2. So the conduction electrons or the itinerant electrons have to form a 4x4 Hamiltonian. This is a 2-dimensional, this 1-dimensional, this they form a 4x4 Hamiltonian. And the Hamiltonian, from symmetry reasons, has to look like this. Okay. And now you can see immediately what this Hamiltonian is. You can compute these values. We computed them first numerically. Now you can compute them analytically. These are the values. You can see that this mass M, which gives you the splitting of these 2 representations, gamma 1, gamma 2, which is actually the bandwidth of the Bistritzer-MacDonald bands. You can see it here as this bandwidth. This mass is very small, okay? And you can clearly see the band structure of this. Now, you can remember then the band structure of this is the band structure of AB untwisted bilayer graphene. Right? So if I take AB Bernal stack graphene, I will get a double Dirac node at the K point. And this double Dirac node is this guy, is this gamma 3 representation. This is the double Dirac node. And these other gamma 1 and gamma 2 are the extra bands. So this is exactly the low energy model of the AB unstacked bilayer graphene. So now we've solved the topology problem. Why? Because I told you that topology comes from having 2 Dirac fermions, 4n plus 2 Dirac fermions, or 2 Dirac fermions. The flat localized bands, they have no Dirac fermions, they're topological, but the this conduction bands have a double vortex here. This double vortex is just exactly 2 Dirac fermions coupled together, put on top of each other. And this carry this topological conduction fermion carries the topology of the bands. So we now have the heavy electrons and the flat and the conduction electrons. So now we have to couple the two parts. And the coupling of two parts can also be understood by symmetry. Okay? Has some form that is given here. Okay? And you can basically understand it just by a constant. Forget about this term, it's small. This constant is actually quite large, it's around 20 electron volts. So this constant is the coupling between the gamma 3 representation of the f-electron and the double vortex is just the coupling between this guy and the f-electron. And this is large. And this will give rise to the band gap of the Bistritzer-MacDonald model. So now we have, and you can get these now all analytically. So now we have a simple model for the twisted bilayer graphene, is that a very localized electron sitting on the AA sublattice of the Moiré lattice coupled to AB untwisted bilayer double vortex electrons sitting on the AB sublattice or around the AB sublattice. They're delocalized, right? But you cannot really say where they sit. So we can ask, how good is this model? Well, first of all, at its very best, if you want just energetics, you can get by with a 6x6 model. And the Bistritzer-MacDonald model has actually an infinite number of shells. You, of course, cut off numerically at some point. But this is a very simple 6x6 model. Notice this is the Hamiltonian. This is the heavy-fermion part, heavy-fermion block, the hopping between the Vanya states on the triangle lattice is 0, 0.1 electron volts, but we call it 0. This is the conduction electron. Okay, and neglect this term, is small. This is the f-electron to the conduction electron. So now it's become a very simple model. So you might think, well, it might do a very crappy job at fitting the band structure or the wave functions. Now this is how the band structure is fit. The red dots are the Bistritzer-MacDonald model. The black lines are our model. Now the fitting does get worse here, okay, at higher energies, but those higher energies are not where the physics happens. And we could actually improve that fitting by taking more terms than just linear terms in this model. But you can see how remarkably well this model does. So now this blue is the double vortex AB untwisted bilayer. This red is the heavy fermion. You couple them, and what you can see is that this difference between the gamma 1, gamma 2 representations, which is just this mass term, becomes the bandwidth of the Bistritzer-MacDonald model, and the coupling between gamma 3 represent between the heavy fermions, this red, and the blue, which is this gamma just becomes basically the gap of the Bistritzer-MacDonald model between the flattish bands and the next bands. So this is the largest term in the system. This gap is the smallest term. So right now we're done with the main message, which I wanted to say, and maybe I can stop for some questions if there are. If not, we can just dwell in the interaction part, and I'll just go much faster to show you why this is a good thing to do now. Very good. So if there's no questions now, why is that a good thing to do, to separate the physics in this way? Well, now you know which electrons are important for the interactions and which electrons are spectators for the interactions, and which electrons carry the topology and which electrons don't carry the topology. So how do we use this? Well, in the interaction terms, you can compute them. You can just do density interaction and compute their values. And what you get is the following. There's several interactions terms, but the most important one, as predicted, is the density interaction of the f-electrons, these heavy electrons sitting on the AA on the triangular lattice. This is by far the largest energy problem, the largest energy value in energy scale of the problem, larger than the hybridization between the F and C electrons. So from the heavy fermion problem, from the Anderson model, you might remember that there are useful models if the coupling between the heavy and light electrons is much smaller than the Hubbard U of the heavy electrons. And this is indeed what is the case here, computed numerically and now analytically. So this is the largest energy scale in the problem. Then you have some other Coulomb scale between the conduction electrons. We can just neglect this. This is important for different fillings. You have a density interaction between the f-electrons and the c-electrons. This density interaction actually just acts as a chemical potential for the c-electrons. And the term that's the most important for the topology of the correlated insulator that comes in is actually a what will be a ferromagnetic Hund's coupling between a higher symmetry spin of the f-electrons and the c-electrons. So most of the physics of this model can be understood with just these three terms plus the three terms with the arrows plus the interaction plus the heavy fermion single particle physics. And let me just give you some example. The first thing that I wanted to show you is that there's a large symmetry in this model, and the large symmetry in this model is actually reminiscent of some large symmetries that other people like Kang and Vafek showed in the projected models, which are strong coupling models which only project into the flat bands. The advantage of this is that these symmetries now actually commute with a full Hamiltonian, with a kinetic part also. So for example, if I take what we call the flat limit, so this mass term, which was the bandwidth of the Bistritzer-MacDonald model, which is 3.7 electron volt, something like this, times 2. If I take this to be 0, then you'll get a U4 symmetry in this model. And this U4 symmetry is nice. You can get the generators, but what's the nice thing about this U4 symmetry is you can write this term, the J term that I told you creates the topology, as a ferromagnetic coupling between the U4 spins of the f-electrons and those of the c-electrons. So now we have a much nicer, still neglect this, so now we have a much nicer form of the Hamiltonian, Hubbard U of the f-electrons, density of the f-electrons, density of the c-electrons, and local U4 moment of the f-electrons times the moment, times the itinerant moment, U4 moment of the c-electrons. And now I'll have to go very fast to this. If you go through this, you can understand basically the physics immediately. What happens in the interacting state is the following. At a given filling, what you want to do is to fill up the heavy electrons, such as to minimize the Coulomb energy. What you're going to do at every filling, the filling is going to be controlled by the heavy electrons. And for example, this is charge neutrality. So I have in these flat bands, I should have 4 electrons in these flat bands, right? They go from -4 to 4. At charge neutrality, I have to fill them, which is 0. I have to fill them with 4 electrons. These are the 4 electrons. This is a parent trial state, okay, where the filling is just controlled by the f-electrons. And this is the Fermi C of this gapless double vortex. Okay, this is the trial state. And the way you fill up these f-electrons, there's many, right? There's valley, spin index, etc., is actually given by Hund's rule on the U4 spin of these f-electrons. And there's many rotations then, and these rotations of these f-electrons have different names in the literature. Kramer valley coherent state, valley polarized, all kinds, intervalley coherent states, etc. So these are just some U4 rotations of this. And when this parameter m was 0, these are, all these multiplets are exact. Well, they should have the same energy. And when it's not 0, they don't have the same energy. And before, there was no nice way of understanding which one would be lower. But now, by just simple rules, there is a way of understanding which one's lower. So you take this trial state and you run one-shot Hartree-Fock, which turns out to be amazingly consistent with self-consistent Hartree-Fock. And one-shot Hartree-Fock can do analytically. So what happens here is very easy to understand. Let's look at this plot. This is and I'll finish up to this. Basically, it's how and by the same token, you get all the interacting states. So what happens here is you started with this. Let's start with the f-electron to c-electron coupling turned off, but now fix the filling by occupying f-electrons, the heavy electrons, to minimize Coulomb. That moves the f-electron bands up and down. Okay, it moves them like this. And then you get this band structure, but now turn the F to C coupling on, and now you'll get level splitting, and there will be a gap opening here because of the J term. There's a level splitting here, and because of the J term, there's a gap opening here. Okay, so this is of order U1. This is of order J. And of course, this charge excitation spectrum looks very similar to just basically heavy fermions moving into the light fermions and then hybridizing with them. By the way, this charge spectrum is almost identical to the one obtained by strong coupling methods, in which you just project into the flat bands, and this procedure becomes exact, with the exception that these strong coupling methods don't get these extra bands here, which could be important. So you can do some math because it's one-shot Hartree-Fock. Now things are very simple. You can actually obtain an analytic Hamiltonian, and you can have the following rules for creation of ground states at every integer filling in twisted bilayer graphene. The f-electrons from the highest weight representation. This is a 100 rule, U4 100 rule, and the state then that wins in this U4 multiplet. So this U4 multiplet is only true when this parameter n is 0, but n is not exactly 0. Twisted bilayer graphene is 3.7. Then the state that wins from this U4 multiplet is the one that's given by the minimization, by the maximization of the gap that opens in the conduction fermions, which is just this this expression where OF is the density matrix of the f-electrons. So depending on which state you build out of the f-electrons at a given filling, this matrix is going to have some density matrix is going to have some expression, and the expression that it has might commute or not commute with the mass term, and then it might lower the energy or not lower it even further. So I claim that with this, you can explain all the results obtained in twisted bilayer correlated insulator states, including the topology. The topology is basically, these Chern insulators are basically the fact that the double vortex has now gapped with a mass. So if it's gapped with a mass, depending on what type of mass you have, you're going to get a Chern insulator. But the last slide that I wanted to show, actually, sorry, the last slide that I wanted to show, if I have it here, is that the power of this approach, it's not, my resume share doesn't work. I just want to show last slide. Let me just reshare again. That the power of this approach actually is becomes evident in the multi-layer systems. So in the multi-layer systems, there's no actually even strong coupling analytical approaches. There's actually 2 Hartree-Fock papers, and some of the Hartree-Fock papers, and one of them, which is ours, we don't understand everything. I won't comment about the other one, but I don't think they understand everything either. So especially some of the states. But now with the heavy fermion model, you have a very simple model which turns out to match the band structure of twisted trilayer graphene, even in electric field, and this is the extra thing that they have in twisted trilayer graphene, they can apply an electric field, a displacement field, and now change things. And you can see that in twisted trilayer graphene, the interesting thing is the appearance of an extra Dirac, high velocity Dirac fermion at one of the K Moiré points. So if I didn't have this guy, it would be basically similar to the twisted bilayer, but I have this guy, which couples to the bands, and the displacement field actually pulls the Bistritzer-MacDonald flat bands away and tries to link them with the Dirac. Now, what I want you to see is that the red and the blue lines are the heavy fermion model versus the actual Bistritzer-MacDonald type models that are used for these trilayers. And you can see the matching is excellent. And now, having done the unpublished interacting physics, because of the separation of scales of where the interactions sit in the heavy fermions and where the itineracy sits, we can understand much better the entire phase diagram of at least the insulating correlated states in the trilayer system. So with that, I thank you for your attention. I hope I've convinced you this is something useful.
Thank you, Andrei, for this excellent seminar. Let us thank our speaker.
Thank you.
And we have time for questions.
So may I ask a question? May I ask a question?
Yes, please go ahead.
Can you say a word about superconductivity?
Yes, so that's much. Yes, so that's very important, and that's much harder. Now, what I can say is the following. So if you have, in the previous strong coupling expansion, if you just project to the strong coupling and have no kinetic energy, you can prove a theorem that if I just project to strong coupling and have no kinetic energy, even though the bands are topologically non-trivial, so the projection will create some non-commutative matrix elements in the interaction model. So it won't be just a simple Haber model, just a simple Haber model with zero kinetic energy, right? If I had a simple Haber model with zero kinetic energy, I could solve everything. But unfortunately, here when you project, because the bands are topological, you get matrix elements, the Hamiltonian becomes complicated. However, you can still solve some things by a procedure first given by Vafek and Kang, and then extended to excitations by us and Vafek and Kang, Alan MacDonald and Zalatan and others. So what you can prove is the following. So what we proved is that for the charge 2 excitation in the system, there is no bound state. You cannot have bound state. So Latinger-Kohn does not exist purely because of interaction elements in the Hamiltonian, in the interacting Hamiltonian non-commutativity. You have to have some kinetic energy for Latinger-Kohn to exist. So there's no, so you see, this is the 2 charge excitation. You can prove by positivity, basically positive semi-definiteness, that there's no, you cannot have a bound state here. So if I don't have, so in projected models, you couldn't get superconductivity. You need to add kinetic energy. Now, the hope here is that you already have kinetic energy, so you don't need, you have a model where you can understand the correlated states starting from a kinetic energy, you separate the scales, so you could possibly understand superconductivity, and of course superconductivity appears in like these Anderson-Konda models. Now, that having been said, we've been working on trying to get the superconductivity here for about 7 months, and the results, the unpublished results are the following. While I had high hopes for phonons before, we now find, well, in collaboration with Xiaoxing Liu and Rishida Song and with other people, that phonons, we just cannot get superconductivity with phonons. So in fact, we can show that if phonon superconductivity existed, it would have to be nematic, it would have to be gapless, but it just doesn't exist because the Coulomb is too large. Now, the one redeeming possibility is off-site superconductivity in the f-electrons, because the f-electrons don't have, their interaction is on-site. They're very localized, but off-site, the interaction falls off dramatically. So we're exploring that possibility, but we don't have much more things to say, unfortunately. Thank you very much.
Thank you.
Okay, do we have any other questions from the audience? It seems not. So in this case, let us thank our speaker again.
Thank you.
And with this, we conclude our today's PCS